Hi guys, welcome. Um, this is a mini e-lecture for module CM3292. Although it's really applicable to a whole range of the chemistry modules here, um, it's a little different to most of the other mini lectures in this series. I'm not describing a piece of equipment or a technique. I'm actually more talking about the stuff, the skills that you need as a scientist. So the sampling mini e-lecture was one like this as well. Okay, what's the difference between you mastering and understanding what research questions are and using them and not? Well, maybe the best way to put it is, first of all, it's part of your growth as a scientist. Those scientists that do know how to frame and develop and then execute their research questions tend to be the more effective scientists. So I'd suggest to you that that's one of the sort of scientists that you probably need to be. Okay, so the aim of this lecture clearly is for you to grasp and be able to use a particular technique. We're going to talk about research questions. I'm going to present you with a silly thing called the fairy godmother. It's just a scheme. It's one that I use, but you may choose others. Then we'll have a closing summary. Now, who do I know that's talked sense about research questions and that actually one might trust to know what they're talking about? I think Richard Andrews, his little book, Research Questions, it's about the social sciences, but pretty damn good actually. I'd go with that one. I think a lot of what we talk about is mentioned and developed much further in that book. Oh dear, I feel like I'm blushing again. Watson Halliwell, useful, is it? Particularly in the first couple of chapters, it's not talking about the social sciences, it's talking much more about the physical and environmental sciences, and you might then find that more useful. So, okay, that's the references. I think the next thing is for us to move on into the content. So, how do you ask good questions and how do you formulate research questions? Well, as with many areas in chemistry, I'm going to suggest that there are definitions, specialist definitions to those terms, research questions and good questions. I'm going to define a good question is one which is a substantive question, but it may be general. So, for instance, what is the nature of gravity? Is a general question, but if you're a physicist or interested in the history or future of the universe, it's a pretty substantial question. Maybe a 7-year-old child could ask it, but and it may not be substantial, but in the hands or in the head of an appropriately trained scientist, it's definitely a substantive question, but it's probably fairly general. A research question, on the other hand, is a good question, so we take as read the fact that it's substantive and relevant, but it's a specific question which can be addressed by obtainable or attainable data, maybe by experiments, and the distinction of a good research question is when it's answered, it actually adds to knowledge. It takes the debate further forward. Generally attributed to Pascal, but very relevant here. Judge a man not by his answers, but rather by the questions he asks, and obviously relevant to what we're talking about here. Time for a quick cup of tea. Okay, so good research questions are usually based in knowledge, often wide knowledge, and often deep knowledge, but not necessarily just deep knowledge. What types of characteristics does a good research question have? Well, they can be written down. If you can't write it down, it's not very useful to you. I won't bother and give you examples and stuff, but it's not enough to say, yes, well, you know what I mean. It's that. No, you have to be able to write it down. Admiral Rickover, and this actually is on my notice board in my office, said famously, weaknesses overlooked in oral discussion become painfully obvious on the written page. You can make palaces, you can right the world in written discussion, you can right all the world's wrongs. But it's when you come to write it down that you see where the issues are. Good research questions are specified to the degree appropriate to the aim of the question. What do I mean by that? Well, how far is Singapore from Hong Kong? Now, yes, I know they're a world apart culturally in ways like that, but let's stick to the literal distance. Your answer might be, it's about 8,000 k. Or it might be, it's about 3 to 4 hours in a plane. Both of those are answers to the question, how far from Singapore is Hong Kong? It's unlikely that you're going to need to answer the question more stringently, but we come here to the development of research questions. If you mean how far is it from the edge of the Singaporean territorial waters to Hong Kong territorial waters, you might come up with 7853.1 kilometres, about. But it depends. Your question must be specified to the degree appropriate to the aim of the question. So there isn't an immediate right answer here, but you have to know why you're asking the question. That will allow you to specify the question appropriately. Okay, research questions. What else about them is characteristic about them? They are addressable by real and obtainable data, either from an experiment or from some other existing source. It may be that your question is addressable by attainable data. That is data which may not exist but is attainable, in which case you're thinking of an experiment. Anyway, so addressable by real or obtainable data. And once answered, a research question yields an unequivocal result. Let's give you an example. Are you pregnant? Is a direct and quite personal, actually, but never mind. A very direct question. And the unequivocal results are, yes, I'm pregnant, in which case I'm hoping you'll say congratulations. Or no, I'm not pregnant, in which case you'll like to get slapped around the face. But they're unequivocal answers. An equivocal answer is, might be, might not be, not sure. A research question must yield an unequivocal result. If you set up with a research question which yields you a result which doesn't enable you to progress further, that is, it doesn't give you the yes-no result, then that's not a good research question. In fact, I'd say it's not a research question at all. The other thing that research questions yield is future direction. Very, very useful. They tend to move the field forward. Okay, so let me introduce you to the fairy godmother. And this is her. For those of you that come from a different culture to me, I should maybe explain what the fairy godmother is or who she is. When we were little children, our mothers and fathers said, oh, you've got a fairy godmother, somebody who can guide you and somebody who, hypothetically could grant you wishes. And there are a number of nursery rhymes around fairy godmothers. I think Cinderella is probably one of the best known ones. In this particular, the reason I've called this the fairy godmother is this box here. If you use this scheme properly, and particular this box, you'll be able to develop pretty much bulletproof research questions, and your fairy godmother, in inverted commas, will have fulfilled their role. So let's have a look at this process. So we start with a general question, and general questions are not usually good research questions. We have to specify the research question. About what? How? We'll talk about this in a moment. And if we get a specific question, we have to know whether we can get data to address that question. And this is not polite. You push this to the limits. Oh, you can get data. Great. Exactly what data? Where is this data? Where's the website? Or where's the paper? Or who has this data? You push here until you're definitely certain that your specific question, you can get data to address this question. It might be, of course, that your data is actually from an experiment, but we'll get to that in a moment. Okay, so we've got a question and we've got data or an experiment potentially to give us the data to answer the question. This then is really important. Is an unequivocal answer possible? Research questions that don't give you unequivocal answers, bluntly, are a waste of time, and I would suggest that if you have a nice specific question, you've got the data, but the answer you get is not going to be unequivocal, you should go back and re-specify your question. So on these diagrams, typically the green arrows are the arrows that mean yes, and the red arrows are the answers that mean no. So in this case, you would go back to your question, and maybe you'd go back again and then work forward. But assuming an unequivocal answer is possible, then the next question, which is almost equally important, and this is more about when you're having to go to an experiment. Are the results that you would need to unequivocally answer your research question, are they either likely, or are they simple, or rather is it some fiendishly complicated experiment with a massively involved analysis technique that requires the wind to be in exactly the right direction, or that you had eggs for dinner last night for the experiment to work? If the answer here, that your results to unequivocally answer the questions are not simple or very unlikely, again, I would suggest you revise your question. And in fact, if you can't make it, design the experiment or whatever to answer your question unequivocally, and that the results will be simple or likely, you go back up here again, like snakes and ladders. You need to reformulate your question. Anyway, this is just a quick wander around this scheme. So let's assume that the answer is yes. To unequivocally answer my research question, the results from my experiment will be simple and very likely. You then go on to full experimental design. You get your results, which in the nature of the beast leads you to other questions, and you go back round the circle. Anyway, so that's the fairy godmother. Now let's walk through it stage by stage with a couple of examples. Now I'm having a quick slurp of tea. So, if you use this process, and it's only a process, it's not particularly special, rather like the fairy godmother myth, it can't necessarily answer your wishes and give you wishes, but it can lead to enlightenment. And as I said previously, the green arrows are yes, and the red arrows are no. Anything in blue is process. So what I've done is I've taken the first lump of the diagram we were just looking at, and I'll deal with this in a bit more detail. So we start with a general question. Let's have an example of a general question. How big is it? Okay. Not very easy to work with a question like that. It doesn't refer to anything. What actually is it? It doesn't pose an addressable question. Does big mean mass, how heavy it is, volume, or a particular dimension, maybe depth or length? A better question, and so we've started here, we've got our general question. A better question, more specific, would be how long is a piece of string? Now, we're not there yet, but what we've done is if we've turned big into length, which is specific, and we've turned it into a piece of string. It's still not a specific question because we don't know which piece of string or whatever. So we'd still need to go back round here, and we go round here as many times as it takes to get a specific question which is relevant. This process of developing research questions is hard. It takes a long time. And for weaker projects, people never get an answerable research question. And that, I'm afraid, fundamentally undermines the project that's being done, or experiment that's being done. So, rather than just keep going round and round, let's give you an example of a good and addressable research question. How long is the IUPAC, the International Union of Pure and Applied Chemistry, how long is the IUPAC standard meter kept in Paris? So the IUPAC system, meters, kilograms, seconds, each has a standard. And the standard for length is the standard meter. It's made of bronze and it's kept in Paris. So a good question, an addressable question, a good research question would be how long is that standard meter, which is kept in Paris. Okay, so that's the process of specification. We've gone through that now. We've struggled and whatever. Our next thing is let's get a sensible specific question rather than just the length of the standard meter. So I'm going to talk about air quality and air pollution because actually that's my area of expertise. Let's start with a general question. Is the air polluted? Okay, we won't necessarily walk through this as we just did. It's clearly a general question, not a specific question. We'd need to ask when and where and with what. So let's say we're interested in ozone. So is the air, and let's take Christchurch City in New Zealand as an example, is it polluted with ozone? We need to think about this a little bit. And the way that we would have to formulate this question is about the definition of pollution. Pollution is about whether there is more there from human activities is the implication, than would be there by natural sources or natural processes. So our more specific question, a question we can call a research question, is: are the ozone concentrations in Christchurch City significantly greater than what might be expected from natural sources? Okay, so we're on the road to be able to do something useful. We're still not completely there, because we need to think, although we've got a valid question, we need to think about what we can compare Christchurch City to. What is natural sources, or what is unappropriate background, I suppose. So, what are background levels of ozone in Christchurch? Well, by definition, because Christchurch is a city and people live there, we're not going to be able to find very easily what background ozone levels are, because all we can measure are total ozone, which is both background plus human impact. So if we think about it, what we might do is say, well, okay, the air getting to New Zealand comes across 4,000 miles of ocean, the Tasman Sea, Australia, or 10,000 miles from South America, whichever direction the wind's coming from. So what we want is the upwind marine concentrations of atmospheric ozone. People haven't affected those concentrations, and if people weren't in Christchurch, that would be the concentration you would measure in Christchurch. Greymouth is a town on the coast, so it may be something that is useful. Now, okay, all fine and dandy. Can we get data? Well, we can. Greymouth and all cities in New Zealand, the ozone concentrations are measured actually by the regional councils, but too much detail. The data is available in the Ministry for the Environment, the MFE site, and they measure ozone concentrations in Christchurch City, or at least they collate the data, and equally they collate the data from a little town called Greymouth, which is in the far west of the South Island. The nearest thing to it is Australia. So it provides us with a surrogate, if you will, for the upwind marine concentrations. So this data is hourly, it's in Excel format, it's measured in a way which makes them directly comparable. So in terms of, can we get data, and is it the correct data? Do we know where to get it from? Is it comparable? The answer is yes. Data is available and accessible to address our research question. Okay, wait for the technology. Okay, so next question. We've now come out of the top box and we're down actually into the fairy godmother. Forgive the expression. So how do we answer our question? Well, we just compare the two MFE air quality databases to indicate what the average concentration of ozone is in Christchurch and what the average concentration is in Greymouth. We can do a statistical test. I think probably 3 standard deviations is 2 or 3 standard deviations is appropriate, either 95% or 99%. And we can directly address our research question, and if we're doing a statistical test, and whenever I use the word significantly, that's a reserved term, that's code for statistics. As scientists, we can't really make many judgments unless we use statistics as our toolbox to make sure that we're not just feeding our own views into it. If we compare those two databases at a 99% significance level, and the results will either be that they are different at that level or they are not different at that level. So if you like, that would be a way that we could do this. Our question passes, we could proceed. Now, this is in one sense slightly easy. It's a database one. It may be that instead you need to define an experiment. You'll need to go around the full loop, and in which case we would need to think more carefully about what experiment and whether the results were likely or not. So typically you can't here, if you're thinking of an experiment to measure concentrations, it has to be with a real piece of equipment, not some imaginary universal detector. For instance, not for this. Well, okay, for this question, you might be using a. What would you use? In fact, probably an infrared. An infrared monitor would allow you to measure ozone at the levels you would need to. Anyway, okay, so we can continue. This is all looking good. So our question then, are the ozone concentrations in Christchurch significantly greater than what might be expected from natural sources? The answer is yes, unequivocal at the 99% level. Now, other questions spring from that. Well, is that dangerous? Where is the pollution coming from? They might be the next questions that you ask as we go round the cycle here. Anyway, okay, I think probably that's done what I wanted to do. So, closing summary, research questions must be substantive, specify to the degree appropriate to the aim of the question. You must be able to write them down. They must be addressable by real, obtainable data. You must be able to answer them unequivocally, and they lead the direction of your future research. I've already said this. This is not an easy thing. I can think of a number of instances of my life where it took months to develop research questions. That doesn't mean to say you sit there going, oh right, okay, can't think of a research question. There are things you can do, but often it involves with a group of people proposing research questions, having them knocked down, changing them until you actually identify exactly what it is you need to address. This is important in the physical sciences, the natural sciences where we are. If you're in the policy area, even more important there. Anyway, I think probably we've taken enough time here. I hope that's useful, and good luck. I hope you learn to develop good and effective research questions. It may take time, but it will make you a better scientist. And actually, in the long run, your work will be more robust and bulletproof. Okay, take care, enjoy, bye-bye.